Why don't you replace Yoshi? Yoshi, you know, the two of you keep popping in and out. Good, good.
Magic.
It is magic.
Okay,
Bye
let's
bye.
continue
Bye bye.
with the second talk of the morning. A small announcement for the people who are in here. The options to it are Vestibulardo Shopee, Ticoto. These are in the Cantarera Square. Someone could walk you to there, and also Arretado, which is a little bit further away. Also, someone of the organization could go with you if you want. That's typical food from the northeast part of the country. The last one, Arretado. Okay, now the next talk, our speaker is gonna be Gilbert Hector, and the talk is gonna be about connected vanishing cycles and generalized Reeb components in codimension 1 foliations. Okay, you can speak whenever you want.
Okay. Okay, you tell me when I should start?
Sorry.
Okay, you tell me when I should start?
Okay. You can start.
Okay.
Okay.
Ok, so bonjour à tout le monde et joyeux anniversaire à Paul. Ok, so bonjour à tout le monde et joyeux anniversaire à Paul. Does it work, my microphone, or not?
Yes, it does.
Okay, so I will report today on a joint work with Fernando Alcalde and Paul Schweitzer. It started 20 years ago when Paul asked for a generalization of Novikov's theorem. It's a long time ago, but it took us a long time of working to get some result. But in my talk today, so I will recall quickly what's Novikov theorem, state our results in some generality, but just indicate some ideas of proofs in a typical particular setting, what we call regular connected vanishing cycles. So let me recall the classical Novikov theorem. In 1952, Reeb constructed probably the first non-trivial examples of foliations. It was on the tree sphere, and the foliation was obtained by gluing together two of his famous Reeb components. So what's a Reeb component? It's a foliation on the solid torus with the boundary as leaf, a toral leaf, and the restriction of the foliation to the interior is a vibration by planes. Now one can notice that there is some very interesting invariant, namely the boundary of the two disk in the product D2 cross S1. It is a non-zero homotopic cycle in the boundary leaf. It has trivial holonomy, so we can push it to the nearby leaves. And as the nearby leaves are planes, the homotopy class vanishes. So this is a non-trivial vanishing cycle considered by Novikov. Novikov, who in 1965 showed that any foliation of S3 admits a non-trivial vanishing cycle, but maybe it was also Hefliger who noticed this fact. But the main claim of Novikov was any non-trivial vanishing cycle in a tree-manifold is supported by a Reeb component. That means in the tree-manifold there exists a solid torus foliated like the Reeb component I described before. Now, our goal was to extend the second part of Novikov's work, and we extend it in three different ways. First, we consider codimension 1 foliations on any closed manifold without any differentiability condition and considering not homotopical vanishing cycles, but homological n-1 cycles. So they will be non-homotopic to 0 somewhere and become null homotopic when pushed to the nearby leaves. So now let me talk about the ingredients we will use for our theorem. And first we define generalized Reeb component. It is a compact manifold with boundary, with a foliation tangent to the boundary, which is still a union of finitely many compact leaves, whose restriction to the interior is still a locally trivial fiber bundle over S1, with the non-compact leaves as fibers. And the third condition is that the transverse orientation, the orientation of some transverse one-dimensional foliation points inwards or outwards along the whole boundary. Of course, this third condition is trivially satisfied in case of the three-dimensional Reeb components we described before. But in general, it is a non-trivial condition. In this foliation, there is a particular type of leaves which is of interest. It is the fibers of the vibration on the interior of R. We call it the frame of the generalized Reeb component. Now, of course, the usual three-dimensional Reeb component is just a GRC whose frame is the two-plane. Okay, let me give some characterization of those generalized Reeb component. In particular, what are the manifolds which can become frames of generalized Reeb components? And it happens that these frames are exactly the open manifolds periodic at infinity. That is, our limit of projective sequence, which is written on my slide, where C is compact, has non-empty boundary, and the map psi maps C into its interior in such a way that B minus psi of B is homologically trivial. Okay, just one word of how when, our theorem is that, okay, those are the frames, but an interesting observation is that the frame determines the Reeb component up to topological conjugacy. The idea of proof, and I will use this idea later, is that one lifts the foliation to the cyclic coring defined by the cohomology class given by the basis of the interior fibration. And then the interior lifts to a trivial fibration over the interval or over 0 plus infinity, but the boundaries, which are not necessarily connected, lift to a manifold L cross minus a compact subset. Now, if one looks for the action of the automorphism group of this covering on the R twiddle on the total space of the covering, it acts on the transverse factor 0 plus 1 plus infinity as a group of contractions. Such a group is topologically unique. Therefore, R, the frame L, determines completely the GRG up to topological but not differentiable conjugacy. Okay, second tool we need is the analog of vanishing cycles, and we call it vanishing towers. Some vocabulary. Take a foliated map of B cross I, H to MF, where H is the horizontal foliation of a product B times 0, 1, where B is a compact, not necessarily connected, complex, or manifold. And we denote by little theta t the restriction to an horizontal leaf of H. As B is compact, it has finitely many components. Therefore, the image theta B lives in the union of finitely many leaves. And finally, we introduce the homology class of theta B. And now, a map like little theta as before defines a non-trivial vanishing cycle if the homology class of any theta t is 0 for positive t, non-zero for t equals 0. And so we will speak about vanishing cycles or vanishing towers when referring to the map like this. In fact, we will also consider some special vanishing cycles. We will say it is rigid if theta t of B lies in a unique leaf LT, homotopical if it is really similar to the original three-dimensional vanishing cycle, where we take B as the sphere and L as the plane Rn, D, C being just the end disk. I will also use later coherently orientable when imposing some orientability condition, but I will describe it later. Now, when the first observation is any generalized Reeb component supports a canonical vanishing cycle. Here I use this covering I described before, L times 0 plus infinity minus k times 0. The compact Mach C embeds into L by definition. Therefore, also B embeds into L. And there is a canonical embedding of B times 0, 1 into L times 0 plus infinity. This theta twiddle is a vanishing tower by definition. It is trivially vanishing in L cross 0 plus infinity. But at level 0, we remove the compact set K. Therefore, it's no longer trivially vanishing in R twiddle. And to obtain the canonical tower, we just project theta tilde to R. Okay, let me give some examples. Very easy example is take a compact manifold. Okay, I explain it in case of surfaces. take any compact surface with boundary. We can map it into itself, for example, by an isotopy by something isotopic to the identity. This says that the interior of C is periodic at infinity, so we obtain a generalized Reeb component where the boundary, the number of components of the boundary is just the same as the number of components of B and the number of components of the set of ends of L. A non-trivial example is the Whitehead 3 manifold. Now let me state our results. The theorem of Novikov was any vanishing cycle is supported by a Reeb component. Here we will have to restrict. For example, assume the vanishing cycle is rigid or verifies some orientability condition. Then we have exactly the same as the Novikov theorem. There exists a generalized Reeb component such that the map theta B cross I lives in R, and the boundary is just the boundary of this. I'm sorry. Well. And the boundary of this Reeb component is just the union of leaves supporting theta 0 of B. But if I say that there are some restrictions, it is because not any non-trivially vanishing cycle is supported by a Reeb component. Okay, here I explain a general family of foliations supporting this kind of vanishing cycles. Let me just focus on the last one. Any foliation on T2 supports a non-trivially vanishing cycle, inclusive any linear flow, irrational linear flow on T2. That's quite surprising, and that's why it took us a long time to reach to our results, because one did not expect such a situation. Okay, so in my talk I will have three parts following the idea of proof of our initial theorem I will call the Novikov theorem. The first step will be, in the manifold MF, we want to detect the boundary of a future Reeb component. For this, we need a compact leaf theorem, and we give an idea of proof in a particular case, that of regular vanishing towers. I will define a bit later. In a second step, we will want to detect the interior of the Reeb component and show that the foliation on this interior is a fibration over S1. I call it the fibration theorem. And here we restrict against more to so-called connected vanishing towers, meaning that here we assume that the manifold B is connected. But in order to have a really general result without restriction, in a last step, we will show that any connected vanishing tower may be regularized, so that in this talk, I will have a complete idea of proof for the connected Novikov theorem. Any connected non-trivially vanishing tower cycle is supported by a generalized Reeb component. So I start the first main part, how detect compact leaves in the ambient manifold when this ambient manifold supports a non-trivial vanishing tower and cycle. For this, I need to define what are regular foliations, regular vanishing cycles. And for this, you can recognize here a formula which is similar to the formula of the canonical cyclic covering of a generalized Reeb component. The difference being that here instead of L, we have C, the compact piece used to build L by a process of projective limit. Now we say that the vanishing cycle is regular if there exists a map big theta of this set into M, which is bifoliated, and such that the initial theta is just the restriction of big theta to the boundary which is b times 0, 1. So we notice that in particular, in this case, as theta of C is connected, as C is connected, it follows that the image of a big theta T is one leaf. So our regular vanishing cycles will be what I called before rigid, locally rigid vanishing cycles. Okay, now there might be particular cases if we suppose that big theta T preserves or reverse orientation. For example, if each theta T is an immersion. This also I will mention later. Okay, now given such a map, big theta, we observe that big theta we can consider it as a singular chain verifying small theta is the boundary of big theta. So we call it a primitive of theta, and theta we call it a global coherent primitive of little theta. And finally, we will use S theta, the image of C by theta T, the support of the primitive theta T. And now an observation. Here, when defining a vanishing cycle, we say that every small theta T is the boundary of a chain, of a singular chain, let's say. But of course, those singular chains vary arbitrarily. A priori, one doesn't have any control on them. But here, by this condition of regularity, those primitives vary continuously. And so in the first step of the talk, we have this continuous variation. And in the last step, for connected towers, we will show that it is automatically verified. Okay, now to detect the compact leaves, we will use plants averaging sequences. We will introduce some averaging sequence, introduce the support of this averaging sequence. It's a family of minimal sets, and then show that any of these minimal sets is a compact leaf. And the family of those compact leaves will produce the boundary of a submanifold which will be our generalized Reeb component. Okay, for this we need a notion of volume. As usual, the volume of some compact set, horizontal compact set contained in a leaf, is the number of open F plaques needed to cover it, where we fix a priori a finite cover H of M by distinguished open sets. And this gives us the size function of theta, assigning to every t the volume of St, which is well defined. Now, because of this regularity condition, one observes immediately that the size function is locally bounded over 0, 1. But it is not bounded in 0. More precisely, the limit of this volume function goes to infinity when t goes to 0. That's why, because if not, we would have a convergence of bounded compact subset, and the limit would be a primitive of theta 0, showing that theta 0 is 0 in homology, which is contrary to our hypothesis. Okay, now observe that the volume of theta t of B, we can assume it is constant, and therefore the volume of the boundary of St contained in theta t of B is uniformly bounded. Then take a sequence of supports St, for example, all the supports of St. It contains an averaging sequence in the sense of Planck. What is an averaging sequence? It's a family of subsets St whose volume tends to infinity, the boundary being of bounded volume. Such an averaging sequence defines a transverse invariant measure. That's Planck's theory. Now, this measure is supported by a compact subset. And this compact subset, any component of this compact subset, is a minimal set of the ambient foliation MF. And as everybody knows, they are of one of the three types: a compact leaf, the whole of M, or an exceptional minimal set modeled on the transverse Cantor set. Okay, now to locate this minimal set, we observe that any of these minimal sets meets theta 0 of B. So there are only finitely many of them. And now the compact leaf theorem states that if theta is regular, non-bounded, I do not need non-trivially vanishing, but I need positive, and I will say later where this shows up, then any minimal set contained in this limit of the sequence of supports is a compact leaf. Okay, to see this, the argument is homological. To see this, we introduce theta, small theta AB, the restriction of small theta to the product B times AB. And then we define a family of cycles of n-1 cycles. No, of n cycles, sorry. Delta AB is theta B, the primitive at the upper level, minus the primitive at the under level, minus the vertical cylinder defined by theta AB. And because of regularity, all those cycles are trivially null homologous by definition, by construction. And then we get easily our compact leaf theorem. Why? If I want it to be any minimal set to be a compact leaf, I just have to show that it's not cut by a closed transversal. So suppose we have a closed transversal cutting M. After shrinking, I may suppose that this closed transversal does not meet the transverse small cylinder, so that the algebraic intersection is just equal to the algebraic intersection of tau with the two bound upper and below primitives. But now, here I suppose that all the intersection indexes of tau with the primitives theta 1 and theta a are positive. That's why I need my vanishing cycle to verify this positivity condition. Then tau times wedge theta a is bigger than the number of intersection points of tau with SA. But the latter tends to infinity because the minimal set is contained in the limit of this sequence of supports SA. So we get a contradiction proving our theorem. Okay, I will have to remove this orientability condition for the regular compact leaf theorem, but this will be just obtained by splitting the map theta into two parts, a positive and a negative part. What will permit to visualize two sub vanishing cycles, each one being positive, the other being negative, but being both regular and being both regular, and of course one of them being non-bounded because the global vanishing cycle is not bounded. So I can forget about this positivity condition. In a second step, we want to find some in the global manifold MF to find a submanifold R, which will be the future Reeb component. And for this, I restrict, as I said before, I restrict to a subfamily of the previous family, assuming that B is connected. And B being connected, the previous general theorem says that there is only one compact leaf in the limit set of the big sequence sigma. And this we will call F. And we will be wanting to show that cutting M along F, we obtain a compact manifold, maybe two, but anyway, one containing the image of the regularization map of the global primitive, and F contained in the boundary of R. But for the moment, we do not know that F is the boundary of R. And R is the wanted generalized Reeb component. To see this, we look for, in the interior of R, an open subset, an open saturated subset fibering over S1. Okay, to get this, we observe that in R, we have a compact vertical closed orbit, tau, such that for any point in this tau, it is cut by infinitely many supports of primitives. And this will enable us to describe concretely all the leaves, the corresponding leaves, L theta. Okay, why, just roughly, how does one get this tau? I assume, to simplify, that the vertical foliation, any minimal set, is a closed orbit, and there are only finitely many of them. Now I observe that the global primitive big theta defined on this set gamma ck, if I take a point x in k, the vertical path theta x is just defined on a semi-open interval 0, 1, and does not extend to the compact interval 0, 1. Why? Because I have removed the point x times 0. So if it does not extend, this means that the image of this map either is a closed compact vertical leaf, and the map theta x accumulates infinitely many times on this compact leaf Tx, because if not, I would extend to 0. Or second possibility, Lx is a half infinite vertical leaf. But having assumed that the only minimal set is a compact leaf, it accumulates on a compact leaf Ty. And we have a similar result. Lx accumulates infinitely many times on Ty. And that's why taking theta in tau, each time Lx accumulates, passes through the point theta, it gives me a support of primitive St, so that this set is infinite and accumulates on 0. Okay. Now, the leaves through a point theta of tau will define the wanted open subset fibering over S1. Indeed, take the union of all supports with T in theta z, in sigma of theta. The first claim is that the union of those supports is the whole leaf as theta. Secondly, this leaf is properly embedded in omega and closed in omega. It's properly embedded in, sorry, I do not yet have, oh yes, I said that omega is the interior of R. So why do I have this condition? because taking a compact subset of LZ with data in Q, this Q is far away from the boundary F. And therefore, if restricting little theta to an interval small enough, Q does not cut it. So this means that Q is contained in some ST. As this is true for any Q, this means that LZ is the union of ST. Now this leaf has one end, by definition. This end accumulates on F. This means that L theta is properly embedded in omega and is closed in omega. Now let's look at the foliation induced on the saturation of tau by the foliation F. All leaves are of type L theta. They are proper, closed in omega, because closed in a bigger set. This implies that F little omega is without holonomy. Now, each leaf has a trivial saturated neighborhood by those proper leaves. Thus, F omega is a locally trivial fibration. It admits a closed transversal, so it is a fibration over S1. Now we are almost finished. We just have to show that this little omega, in fact, is the interior of R. And this is because, if not, the leaves in little omega would accumulate on some other minimal set. But this is impossible because they accumulate only on F. And the same reason says that the boundary of R is just the unique compact leaf we had got before. So this means that we have proved this Novikov theorem for regular connected vanishing cycles. Now, at the last step of my talk, I would like to remove the condition regular, to say that any connected vanishing, non-trivially vanishing cycle is supported by a Reeb component, generalized Reeb component. And here the idea is, okay, I take any such vanishing cycles, and I will regularize it. That is, I will construct a global, regular, primitive big theta of little theta. And the idea is to proceed in two steps. First, we construct it locally. We say that the vanishing tower is regular over a domain if there exists regular primitive over this domain. Okay, and now the main step in what follows is that any connected non-bounded vanishing tower is locally bounded over a maximal open dense subset eta in 0, 1. This was trivial in the regular case because the variation of the volume function was continuous. And secondly, it is locally regular over a maximal open dense subset theta. And later on, I will just have to show that theta is 0, 1. Okay, so now what's the idea, the proof of this lemma? the boundedness is an argument of bare category. So for the second, I use strongly the fact that leaves of any foliation have generically trivial holonomy. Therefore, I can take a point A in eta, assume that the leaf LA through this point A has trivial holonomy, and produce a nice tubular neighborhood foliated trivially as a trivial product by the restrictions of F and T, and where theta is bounded over UA. Then we are in a product foliation. We have vanishing cycles moving from one level to the other, and of course, taking a primitive at one level, it can be moved to all the other levels. Now, in order to show that data is the whole of 0, 1, I look at a connected component J of data. And roughly speaking, we show that V theta or theta is bounded over G, thus over bar G, so that the global G primitive extends over G bar. Finally, to conclude that data equals 0, 1, we look at the complement kappa of data. It is a bare space. All the previous constructions and descriptions apply to this bare space. So I get a global primitive theta indexed kappa 0 for some Klopen subset of kappa. By unicity, it coincides with theta bar G on each bar G intersection kappa 0, implying that kappa 0 is included in theta, a contradiction. So we have proved that any connected, non-bounded, non-trivially vanishing tower is regular, thus supported by a generalized Reeb component. Of course, we may apply this to a homotopical tower. It is connected, thus supported by a homotopical generalized Reeb component, and we recover the classical Novikov theorem in class C0. Thank you very much for your attentions et joyeux anniversaire à Paul en attendant le 90e.
Oh, any questions?
I would like to make a comment about the very beginning of the talk, when you observed that a necessary and sufficient condition for an open manifold, an open connected manifold, to be a leaf in a generalized Reeb component is that it be periodic at infinity. So you had this, compact connected bounded manifold C with a mapping, with an embedding psi of C into its interior. But the comment I wanted to make is that the Reeb component that will result depends not only on the manifold as periodic at infinity, but also on the mapping psi. For example, if C has several boundary components, they could be permuted. So this is just clarifying that the Reeb component is determined by the pair, the manifold C and the embedding psi of C
Yeah,
into
yeah,
its
of course.
interior.
Yeah, of course.
Of course.
Any other question? Okay.
Yes, so my question, Gilbert, will be about the generality of that this vanishing cycle can be carried by more than one leaf, if I'm correct.
Yeah.
So yes, I would like to see a really interesting example of that.
Okay. Yeah, but of course, we have examples, but they are very tricky. And again, that's one reason why we worked so long on this problem. And okay, I can send you a copy of those examples, but I cannot explain it in 2 minutes. There are too much involved.
With pleasure. In fact, I thought a little about it and never could decide if there were interesting examples or not for these vanishing cycles with several leaves, supported on several leaves. So I'm very interested.
Okay, as I told at some time, there exist such non-trivially vanishing cycles on any irrational linear flow on the torus. That's quite difficult to imagine, I think.
Yeah, but that's also independent from the fact that the cycle is supported on several leaves, because in that case, the cycle can be even supported on a single leaf.
No. It will be supported on several leaves, and this orientation condition will not be fulfilled. There will be components of C oriented positively and other oriented negatively. That's why I said I cannot give the idea of construction just in 2 sentences.
Okay. Any other question or remark? So let's thank the speaker again, Gilbert again.
Thank you very much for your attention.